Having discussed method of joints and method of sections, we now close with an assortment of issues that may arise in our examination of trusses. The three issues we'll address are treatment of distributed loads, static determinacy or indeterminacy of trusses, and buckling and the relevance of zero-force members. This initial slide addresses distributed loads. Our premise in truss analysis is that we can treat the assembly as a set of two-force members. This prevents the imposition of a load between joints. So what do we do if there actually is a load applied between joints? This slide provides a strategy for converting a load applied at an intermediate location between A and B to two equivalent loads applied at A and B. We use our equivalent force system principles to effect the conversion. In the slide, this is shown as requiring the moments about points A and B as being the same in the two different representations. Alternatively, we could have required the sum of F1 and F2 to be the force F, along with requiring the moment about A or the moment about B to be the same in the two cases. The result shows that as we slide F from A to B through distance D, F1 drops linearly from F to 0, and F2 increases linearly with D from 0 to F. The most obvious application of this principle involves incorporating the weight of truss members into our analysis. Assuming the truss is constructed of homogeneous, that is, constant density beams having constant cross-section, the weight of the beam is uniformly distributed across its length, and the effective center of the beam's weight, a concept that will be discussed in Chapter 7, is right in the middle of each truss member. Our conversion principle states we can account for this by taking half the weight of each beam and applying it to each of its joints. There is also a note at the bottom of this slide about the treatment of bending, which involves deformation of truss or beam members normal to their long axes. Bending of a beam requires us to make a transition from rigid to deformable bodies, which we will not be doing in this class. Were we making this transition, we would find the deflection of beam AB would be very different in our two different load cases A and B. It is usually the case that our equivalent force systems principles apply only in the case of rigid bodies. Real structures are extremely stiff along their long axes, however, so they still appear to be rigid even though they are made of deformable material. As our truss analysis involves only axial loads, we can get away with the use of an equivalent force system principle in this case. The next couple of slides address the issue of static determinacy. Some of the trusses in the textbook have tens of members, and actual trusses can have hundreds of members. Since analyzing a truss is time-consuming, we'd like to have a good idea that we'll be able to successfully analyze a truss before we start. This slide presents a rule of thumb for determining whether a truss has partial fixity, that is, it can move, or is statically determinate or indeterminate based on a simple relationship between the number of members, the number of reactions, and the number of joints. To see how to use this, let's go briefly back to example 2 to see how it works. For reactions, we count one reaction component for each degree of freedom that's constrained by the truss. A roller counts as 1 degree of freedom. Since the only degree of freedom restrained is normal to the surface of the roller. A pin counts as 2 reaction constraints. 1, 2. Since both horizontal and vertical translation are prevented. In the present example, we have 1 pin and 1 roller support, so R, the number of reaction components, is 3. For joints, we count every connection between members, including those where reactions are present. In this case, we have 8 joints in A through H, so J is equal to 8. We then count every member, and in this case, we have 13. For this truss, we ask, what is the relationship between M plus R and 2J? Since 13 plus 3 is equal to 2 times 8, we match the conditions for static determinacy, and we can have confidence before we start that we should be able to solve for the axial load in any member. As with our rule of thumb for individual rigid bodies, however, we note that because this is just a rule of thumb and not an absolute law, there may be circumstances where this doesn't give us an accurate assessment of the truss. Nevertheless, it's a valuable and quick tool to have on hand for a preliminary assessment of the truss. Here we have a variety of truss configurations that illustrate the correlation between the rule of thumb and the truss behavior. The first row provides two trusses we wouldn't want to construct. The first has two roller supports, so it is able to slide back and forth freely without violating its restraints. The second, truss B, actually undergoes a combination of movements. Its left side can pivot about the pin, and a clockwise rotation is shown by the dashed lines. In order to be consistent with our assumption of rigid body motion, the right side must simultaneously rotate and slide to the left in a combined translation and counterclockwise motion. Note that the sliding left of the rightmost support does not violate the roller boundary condition, because that only provides a constraint normal to the supporting surface. The second row shows typical configurations of statically determinate trusses. Note that if we were analyzing truss D, we wouldn't want to begin with an analysis of the whole truss, as that would be statically indeterminate. Here we would be better off by starting with an analysis of the upper joints. The third row shows two trusses where the rule of thumb does not provide an accurate assessment. The rule of thumb predicts static determinacy, but both trusses are statically indeterminate and have partial fixity. That is, they are capable of moving. Truss E is able to slide back and forth freely. Truss F is more complicated. Although no loads are shown on truss F, it isn't difficult to see that the only way it can support loads is through significant deformation. Consider vertical loads applied to the two upper joints. Analysis of those joints will require all the non-horizontal members to be in compression. Analysis of the bottom center joint then indicates equilibrium is impossible unless the bottom members undergo significant rotation and accompanying deformation, so that the orientation of those bottom members is sufficiently changed that they can counteract in tension the compressive loads brought into the joint from above. So here are the compressive loads that are brought into this joint from the equal and opposite nature of the members that are required to support the vertical loads at the top. And then there has to be a change in geometry here at the bottom so that we get vertical components here able to counteract those compressive loads coming in from the top. So truss F can only be in equilibrium in this case after experiencing significant deformation. Finally, the last row shows three cases where the trusses are statically indeterminate. This includes the very last truss, truss I, which is both statically indeterminate and a mechanism because of the 3 roller supports along its bottom. As discussed in earlier parts of the class, buckling is a catastrophic failure mode that must be avoided at any cost. Buckling is a failure mode that occurs only in members in compression. There is nothing analogous for a member loaded in tension. Buckling is a kind of elastic instability that can occur with the wrong combination of loading and geometry. The movie shown in this slide indicates what happens. Here we are applying a vertical force P to a yardstick. It's important to note that load P is increasing. Initially, we can increase P without seeing any additional deformation in the yardstick, but at some critical load, P critical, we get a snap-through type failure. In the summer of 2007, a span of bridge across I-35 near the Twin Cities collapsed suddenly. We can think of this as a kind of environmentally assisted buckling failure. Here the traffic load was not necessarily increasing, but the geometric integrity of the bridge was gradually degrading from corrosion and other environmental factors. There was no warning when the bridge failed. People were simply driving across it one minute and plunging into the river the next. This illustrates why buckling is such a concern. No warning is given, and the accompanying collapse typically results in total failure of the structure and loss of life. The actual treatment of buckling must be examined in the context of a deformable body. As that is beyond the scope of this class, we replace a real vertical column with a contrived assembly. 2 rigid bodies connected by a torsional spring. Here, all the flexibility of what is normally a continuously deformable body is lumped into the spring. This model won't provide the right scaling, but it gives us some insight into the bifurcated nature of buckling. Examining the free body diagram in C and taking moments about B, we obtain the equation minus 2k plus PL over 2 quantity times theta is 0. This has 2 solutions, one where theta is 0 and P can take on any value, and one where P takes on a special value and theta is free to assume any value. The transition between these 2 solutions represents the snap-through type of failure we observe in our movie. In our model case, the critical value of P scales inversely with L, the unsupported length of the yardstick. When we use methods appropriate to real deformable bodies, our expression for critical buckling load scales inversely with the unsupported span squared. In fact, the expression looks more specifically like P critical equals a parameter alpha times this collection of constants, E times I divided by L squared. Here, alpha is a dimensionless number that depends on precisely how the ends of the span are supported. It is a different number if the ends are pin supported, for instance, than if they are fixed. It is typically on the order of 1 to 10. The quantity E is a material property. It is very large for steel, of moderate size for concrete, and small for wood. It has the same units as pressure, Newton per meter squared, or PSI. The quantity I is something we're going to be evaluating in Chapter 10. It is called the area moment of inertia, and it has units of meters to the fourth or inch to the fourth. We'll talk more about its importance in buckling when we get to the end of the class. Finally, we have the unsupported span squared in the denominator. Inserting the units of E, I, and L into the expression, and using the fact that alpha is dimensionless, you'll see we get, from the right-hand side, a load in newtons or pounds. What is most important for us in this expression is that the critical buckling load scales with the unsupported span squared. We want the critical buckling load to be as large as possible. Long, slender members are vulnerable to buckling. Short, squat members are not. If we can break a long member into two members each half as long as the original member, we have increased the critical buckling load by a factor of 4. Herein lies the value of our zero-force members. Even if it isn't carrying a load, a zero-force member can break up an unsupported span into two shorter members, substantially increasing the critical buckling load of each of them. Of course, this only works if the members are in compression. When we evaluate a truss for the potential removal of a zero-force member, it is crucial to determine whether the removal of the zero-force member would increase the unsupported span of a compression member. If so, it's important to leave the zero-force member intact. If not, that is, if the zero-force member is simply breaking up spans in tension, the zero-force member can be removed without jeopardizing the integrity of the structure. To close, we return to two trusses examined earlier to see if the removal of zero-force members is permissible. Here we have a truss examined in section 6.1. We noted then that member CD is a zero-force member. We also determined as part of our analysis that members BD and DF were carrying compressive loads of 8 kips. In this case, we would not want to remove CD, since it would decrease the critical buckling load of what would be BF by a factor of 4 relative to BD or DF. Here we have a truss we examine in conjunction with the identification of zero-force members. Let's take a moment to identify those zero-force members as well as indicate the members experiencing the same load based on collinear equilibrium component equations at the accompanying joints. So we had previously found that BC and JK and BE were zero-force members. And because of the examination of equilibrium equations around C, B, E, and K, we had found that these three members all carried the same load. These two members carried the same load. And these two members carried the same load. Even though we didn't have specific numbers for the forces, we can still draw conclusions about which, if any, zero-force members can be removed, assuming the applied loads are vertical and downward as shown in the slide. Imposing equilibrium on the whole structure will eventually give us the vertical support reactions at A and L. Examination of joint A indicates member AB must push into the joint in order to counter the vertical force provided by the reaction at A. Member AC must then pull on the joint to counter the horizontal component of member AB. This indicates that AB is in compression and AC is in tension. Because of the results of the collinear equilibrium component equations, AC, CE, and EG are all in tension, and BD and AB are both in compression. A similar examination of joint L indicates HL is in compression, and KL and IK are in tension. Now we can determine which zero-force members to remove. Removal of BC and JK can be accomplished without incident because both of these members are breaking up tensile spans. Member BE, however, is breaking up a compressive span, so it should be retained. In closing, we've learned two different techniques for analyzing planar trusses as well as some things that can help us simplify our analysis. The techniques and observations we've made in planar trusses can now be applied to 3D trusses, which we call space trusses.